Now the next area I want to cover is frictional losses. Now when water flows down a hose, it will create friction, and this will result in a loss of pressure at the end of the hose, and this is due to the particles rubbing against the edge of the hose. Now clearly when no water is flowing in the hose, if a pressure gauge were placed at various points, it would read the same. Now when it's flowing, it will be higher at one end than the other because of frictional losses, and this is created as the particles bounce against each other and as they rub against the internal surface of the pipe they are flowing through. Now clearly the friction factor of different hoses, it will be different, so some hoses have got a lower friction factor than others depending on how smooth they are. Now clearly this frictional loss will be seen as a pressure drop at both sides of the hose. Now there's a few rules regarding frictional loss which you should be aware of. First of all, frictional loss varies with diameter. If you double the diameter, you halve the frictional loss. Frictional loss is proportional to the roughness of the internal surface. This is where you see a friction loss factor identifying how smooth the actual hose is. And frictional loss varies directly with the length of the hose or the pipe. If you double the length, you double the frictional loss. Frictional loss is independent of the pressure. It doesn't matter what the pressure is, it will have no impact on the frictional loss. However, what is important is the velocity of the water. The frictional loss varies with the square of the velocity. This is a very important factor because if you double the velocity of the water, you increase the frictional loss by a factor of 4. On the same point, if you can halve the velocity, you can reduce the frictional losses to 25%. This means if on the fire ground a fireman twins the hoses from a fire appliance, it will halve the velocity of the water and reduce the frictional loss to a quarter. Now, there are a number of formulas that can be used to determine the frictional losses experienced as water flows. And this is the first one here. The head loss due to friction here, HF, equals 2FLV squared divided by dg. Like I say, where HF is the head loss due to friction, F is the friction factor, L is the length in metres, V is the velocity in metres a second, your D, your capital D, is the diameter of the hose, and your G is acceleration due to gravity. Now this can be converted by converting head into pressure to change it around into this, where PF equals approximately 20 FLV squared divided by G, where PF is the pressure loss due to friction in bar, F is the friction factor, L is the length in metres, V is the velocity in metres a second, and D is your diameter. So you've got a HF and a PF, two different formulas that you can use to work out the head loss due to friction or the pressure loss due to friction. Let's do an example applying this formula. Now, a pump is supplying a branch at 5 bar pressure. The branch is at the end of 6 lengths of 25 metre hose, which has a diameter of 70 millimetres and a friction factor of 0.0013. If the velocity of water is 8 metres a second, what pressure is required at the pump? Well, the first thing to do with this is to draw out the problem. This is what we have to do, draw out the problem. Now what we have to determine is what the frictional loss as the water travels down the hose and add this to the pressure at the nozzle. So right, which formula do we know that includes all these parameters? Well, this is the formula here, this one here. PF equals 20 FLV squared divided by D. All we need to do is put in the parameters. We put them in, these parameters as you can see here, and this multiplies out to 3.57 bar. Therefore, to supply the branch at 5 bar, we need to provide 8.57 bar at the pump. Let's do another example. A pump is supplying a branch at 4.5 bar pressure. The branch is at the end of 4 lengths of 25 metre hose, which is a diameter of 45 millimetres and a friction factor of 0.0012. If the velocity of the water is 6 metres a second, what pressure is required at the pump? Now the first thing this is to do is to draw the problem out, and this is what we have. Now what we have to determine is what the frictional loss as the water travels down the hose and add this to the pressure at the nozzle that we require. So right, which formula do we know that includes all these parameters? Well, this is the formula here again, 20 FLV squared divided by D. All we do is put in the parameters, as you can see here, all these are known, and it multiplies out to 1.92 bar. So if we add 1.92 bar to our 4.5 bar that we need at the nozzle, we've got to provide 6.42 bar at the pump to achieve that. Let's do another example. A pump is supplying a branch at 4 bar pressure. The branch is at the end of 5 lengths of 25 metre hose, which has a diameter of 45 millimetres, and it's got a friction factor of 0.001. If the velocity of the water is 4 metres a second, what pressure is required at the pump? Now the first thing again to do is draw out the problem. This is what we have. Now what we have to determine is what the frictional loss is as the water travels down the hose, and again add it to the pressure that we require at the nozzle. Which formula do we know that includes all these? Well, here it is, PF equals 20 FLV squared divided by D. This multiplies out by putting all your parameters in, all your known parameters. It comes out at 0.88 bar. If we add that to the 4 bar that we need at the nozzle, we need to provide 4.88 bar at the pump. Now the most important fact to remember is that frictional loss is proportional to the square of the velocity. So if you want to reduce the frictional loss, you need to reduce the velocity of the water, and that is by using larger diameter hoses or twinning the hose. Let's do another example. A pump is supplying a branch at 4 bar pressure. The nozzle at the end of 5 lengths of 25 metre hose, which has a diameter of 45 millimetres and a friction factor of 0.001. If the velocity of the water is 10 metres a second, what pressure is required at the pump? Again, the first thing is to do is to draw out the problem. This is what we have. Now what we have to determine is what the frictional loss as the water travels down the hose and add it to the pressure of the nozzle. Right, which formula do we know that's got all these? This is the formula. PF equals 20 FLV squared divided by D. You put in your known variables and it multiplies out to 5.55 bar. Therefore, to supply the branch at 4 bar, we need to provide 9.55 bar at the pump. Well, clearly this is not possible, as you would not generally get higher than 8 bar from a pump. So you won't be able to supply that pressure at the nozzle. Now, the main problem here is the velocity of the water. The frictional loss is proportional to the square of the velocity. Now, if we can halve the velocity, we can reduce the frictional loss to 1/4. So, what would be the impact if in this situation you twin the lines and had 2 branches working with the same output of water? So by twinning the lines you halve the velocity of the water. So all you do is you go back to your formula now, and if we've halved the velocity, put in your frictional loss in the formula there, PF equals 20 FLV squared divided by D, you put it out, this multiplies out now to 1.39 bar. Do you see, by halving the velocity you've reduced the frictional loss to 25%. Now we have twin lines, so we have to double the frictional loss to 2.78 bar. So to supply 2 branches at 4 bar, we have to provide 6.78 bar at the pump. Because they're both going to lose some frictional loss, you do have to add it. That's the answer to that. So you can achieve it now. Pumps will be able to achieve that. Let's do an exercise. Water is flowing through 120 metres of 45 millimetre hose at a velocity of 5 metres a second. The pressure at the pump is 7.5 bar, and it's been identified that 15% of the pressure is lost between the pump and the nozzle. We want you first of all to explain firstly the purpose of the nozzle, and secondly why pressure is lost and its value. So we need to work out the value. Well, first, let's go for the first part. The purpose of a nozzle is to convert pressure energy into velocity energy. Remember the formula, Q equals VA. Clearly, if the quantity of water is the same, if you reduce the area of that outlet, which is what a nozzle does, it increases the velocity of the water. And this is the purpose of a nozzle. It reduces area, increases velocity, and it gives water the oomph to be able to project large distances. That's what you've got to do. You've got to give it some velocity. So that's part 1. The second part of the question asks you to explain why pressure is lost in the hose. Well, this is down to frictional losses as the water travels down, and like I say, it's proportional to the smoothness of the inside of the hose, internal roughness, and the number of factors that do account for frictional losses. Best thing to do now is work out what the frictional loss is now. What is the frictional loss? Well, this is the formula we need. PF equals 20 FLV squared divided by D. Now we need to transpose the formula to express it as F, the frictional loss. That's what we're trying to work out now, the frictional loss. This transposes to, if you transpose it, F equals PF times D divided by 20 LV squared. Do you see what we've done? We've transposed it and expressed it as a friction factor now. Well, we know that the pressure loss due to friction is 15% of 7.5 bar, which is 1.125 bar. Now, if you put in all known variables, which you know, it's giving them all formulas, F equals, these are the known variables, it gives us a friction factor of 0.000084375. You have just worked out the friction factor and you've just solved that exercise.